In this video, I'd like to discuss a simple example of frictional forces, and this is due to kinetic. So I'd like to discuss static and kinetic sliding forces of friction. It's a big mouthful. Friction is not very well understood. We don't have models like atomistic models like from quantum mechanics or something low level to explain friction. We don't have a full understanding of friction, but we have simple models, right, that seems to explain some forces, and one of them, right, that most people discuss in college and university physics, right, is static and kinetic sliding forces. So imagine the following. We have a box, and this box, right, I apply a force of, let's say, 10 newtons. This box is very heavy. Maybe it's like 100 kilograms. So it's a very heavy box. And maybe the surface, right, is so rough that this box doesn't move. So when I apply 10 newtons of force, right, on this 100 kilogram box, right, it doesn't move. This force, right, must be neutralized by some other force, and that's basically due to something called static sliding frictional force. So there is a static force, right, that's pushing back to my 10 newtons, and we'll call this, so if I could imagine there's a resistance force, we'll call this FR, friction. This frictional force, right, when I apply 10 newtons on the 100 kilograms, there's a frictional force that's acting in the opposite direction that's also 10 newtons. Of course, it's acting in the opposite direction, and I can't really equate a vector with a magnitude. So, but let's just take the arrow off. So there's a frictional force. So if I apply 10 newtons, there's a resistant force of 10 newtons also. If I increase it to 20 newtons, there is a reactionary force, and that's friction. The frictional force is also 20 newtons. If this did not balance my force, right, everything that I applied, then this object would be moving, because that's actually the second law of Newton. Newton's law says that sigma F is equal to ma. So if this is not moving, the acceleration, so remember, sigma F, the sum of all forces acting on an object, is mass times acceleration. If I apply a force and this object does not move, that means the acceleration is zero. That means that there's forces acting on it that's causing it to be neutralized. The force that I push is being neutralized by this force of friction on this block interacting with the surface. This frictional force, right, is referred to as a static friction, or a static frictional force. What's really interesting about a static frictional force is that if you keep pushing harder and harder and harder, right, at a certain point, right, this object starts moving. And once it starts moving, right, it's much easier to push the object. So for example, you're pushing a car. Initially, the car doesn't move, and you push and push and push, and then suddenly, once it starts moving, it's much easier to push the car. Same thing in here. We have a box, and initially when you apply a force, nothing happens, but the minute it starts moving, because I pushed it really hard, then it starts easier to push it faster. So initially, when the object is not moving and I apply a force and the object still stays not moving, that's due to a frictional force, and that's called a static friction. If the object is moving, so let's imagine that I apply a force and I exceed a certain point, let's say 100 newtons, and it starts moving, then you'll find that the frictional force, right, suddenly drops off to a lower value. You'll find that once I apply 100 newtons, if it was static friction, there would be 100 newtons pushing back on me. But once it starts moving, the frictional force will actually be smaller. Maybe it's 80 newtons. So it's kind of strange. So initially, when the object is not moving, the static friction, right, basically says it has to balance my applied force. But once it starts moving, then the frictional force drops off to something smaller, and that force, right, is referred to as a dynamic frictional force. Or, I'm sorry, a kinetic frictional force. Now, we don't fully have a good model for explaining these details, but initially in the college and university physics, in your introduction to physics, what we do know is that the force of static friction, I'll call it Fs for static friction, has a maximum value. This is always less than or equal to some coefficient called the coefficient of static friction times the normal force. So this is the normal force. And this mu, it's called mu s, is the coefficient of static friction. But once we have it's moving, I'll call it Fk. The frictional force that starts acting backwards, right, is again related to the normal force, which is given by the coefficient of the kinetic friction times the normal force. So this is called the coefficient of kinetic friction, and N is the normal force. These two equations are not perfect, but they're a good approximation of most systems when you have some object sliding across another object. So it's kind of strange, but we don't know where these equations come from, but it's an approximate and seems to work for most cases. So the best way of explaining this, right, is let me give you some examples. But before I continue, you have to understand that the coefficient of static friction is always much larger than the coefficient of kinetic friction. So these two equations, they kind of look the same, mu Sn, and the kinetic frictional force is mu Kn, but usually, well, in most cases, the coefficient of static friction is always greater than the coefficient of kinetic friction. Now, to explain this model a little bit further, right, let's do some examples. And so I'm going to erase all this. And let's try some problems to make sure you understand. So, imagine you have a box. You're told that this weighs 10 kilograms. You're also told that the coefficient of static friction is equal to, let's make it 0.3. I made up these numbers. The question is, what is the maximum applied force before the object moves? So I'm going to apply applied force. I'll call it Fa for an applied force. So, and we're told what is the maximum applied force that I need before this 10 kilogram box starts moving. And I'm going to assume it's a sliding frictional force, so there's a resistance force going in this direction, and I'd like to know exactly what the maximum applied force before the object starts moving. So we know that the force of static friction, the magnitude of the start friction, right, is always less than or equal to mu s times the normal force of that object. And so there's a normal force of pushing this mass right up. So remember the normal force? Normal force basically pushes up the object, pushing up on the mass. So we need to calculate this. So the maximum force, when the maximum force, right, the maximum frictional force of static friction, right, occurs when there's an equality. So this is what we're going to be dealing with. So the resistance force, right, is equal to mu Sn. So again, so we have a rough idea of a diagram. We drew the diagram roughly, and now the next part is I'm going to start drawing the free body diagram. And actually, let me do it over here. I think I have enough space over here. So the free body diagram for the system. Here is your mass, and if you think about it, there is an applied force. Let's call it Fa. That's the applied force that I'm pushing in this direction. I'm also expecting the resistance force, which is backwards. It's pushing against me. That's the force of static friction. I'm also expecting force of gravity pulling down. And then there's a normal force that the surface is pushing on the mass. So that's a normal force. So here's my free body diagram. There's 4 forces acting on the system. I'm also told I'll also be using the direction I to the right and J to mean the unit vector up. So we're going to do our calculations. So all I know is that Fs is to the right. So, well, actually, let's write the second law. The second law is that the sum of forces equals mass times acceleration. But what is the acceleration? The acceleration is 0 because it's not moving. So because it's not moving, we can just say the sum of all these forces. What is the sum of all the forces? We have a normal vector. We have the force of gravity. We have the force of static friction, Fs. We also have the force, the applied force. So I'm trying to find the largest applied force for this to be true. Now we're going to start breaking apart into units. The normal force, right, is N. I don't know, but it's going up, so I know it's Nj. Force of gravity is down, so it's Mg, J. The force of static friction, it's going in the reverse direction, right? It's going backwards in the minus I direction. So this would be, I don't know what that is, but I know that that is equal to, well, actually, let's put it in. We know the maximum force is minus mu n times I. And finally, hopefully this is still on the screen. Yeah, it's still on the screen. That's good. And then the applied force is Fa, and it's going forward, and that's all equal to 0. Did that squeeze in? Kind of. So here is our vector equation that we get. I'm going to rearrange this and write n minus mg j vector plus mu n. So this is the applied force minus mu n I is equal to 0. So remember, these two vectors, this vector, right, is equal to 0, so it means the components are equal. So that means that the normal force is mass times gravity. And the applied force, right, and I'm sorry, I should be actually putting mu s because this is static friction, so I'll use mu s. And so our n is equal to mg, and we also get the applied force is equal to mu s times n. But since I know what mass, n is the mass times gravity, right? Mass of the object times gravity, gravitational acceleration, g. So this is mu s times mass times g. This is the applied force. So the maximum applied force before it starts slipping, right, is given by FA. We bring out our calculator and calculate FA to be coefficient of static friction is just a number, 0.3. The mass of the object is 10 kilograms. I'll use standard units. And the acceleration is 9.8 meters per second squared. And of course, the kilograms meters, eventually you get the answer in newtons. Bring out your calculator, multiply 0.3 by 10 by 9.8. So it's a standard procedure. You're going to see this over and over again, but hopefully you kind of understood. So this is the maximum force. If I apply a force then less than this number, the object won't move. But if I reach this number, right, and just a tad little bit more, it starts slipping. So the object starts sliding across the surface. So notice the procedure, okay? We're always going to find the normal force, right? So a definition of the frictional force. So we're expecting that generally, the frictional force is always, resistance force is always less than mu s, a coefficient of static friction times the normal force. So you're going to see this again. It's always less than or equal to. But once it reaches it, right, it starts slipping. And once it starts slipping, we can no longer use this equation. We have to switch to the force of resistance, right, is a kinetic force, and that's equal to the coefficient of kinetic friction times the normal force. So we have to switch to this equation. So until the object is moving, we have to use static frictional forces. And again, the reality is that these are approximation in real life, right? They do stray from normal. So even if so generally in these models, right, it's a good approximation. In most cases it works. It doesn't say about what the contact surface is. So for example, if I have a box and I half the box, but the weight is exactly 10 kilograms, still the same, right? We'll still find that the Fs, right, stays roughly about the same. So it's kind of strange, right? But it's in a good approximation. It seems to work in most cases, but really, if I had 10 kilograms spread over a large surface, right, I'd expect Fs to be much larger. The static friction, right, of resistance would be much larger. But in reality, it's a good approximation. But so again, this is just a model that seems to work. Good for engineering, but fundamentally why this works, we don't fully understand. But anyway, this is static friction. So let me do another problem with kinetic friction. So imagine that I have a box again, and I've applied a force of 10 newtons, and this box weighs 10 kilograms, and we find that the coefficient of friction, right, is a value of 0.01. So we're told, right, that the coefficient of kinetic friction is mu k, 0.01, and I'm applying 10 newtons of force to push this object. The resistance force is acting in, the frictional force of resistance is acting in the opposite direction of the applied force. And the question is, what is the acceleration? So again, we're going to be, we'll draw a little diagram, and we're going to basically repeat this process to do a free body diagram. It's a standard procedure. You're going to see this in all of these equations, whether you, in most of the problems in Newtonian mechanics, right, we'll always do a free body diagram and repeat this process again. So if I look at the forces acting on, there's a force of gravity pulling down. There's a normal force of the surface pushing perpendicular to that. So there's a normal force. There is an applied force, I'll call it FA. And then there's the frictional force that's kinetic, and I'll just call it Fk. That's acting backwards to the applied force. So here's our four forces again. And we're going to use Newton's second law again. So let me do it over here and maybe create more space. So sigma F is equal to mass times acceleration. And this is what I'm trying to find, so I can't get rid of it. So we'll just call it A. The force is acting on this object. And let me put it in the opposite direction. So mass times acceleration is equal to F vector, sum of all forces. And the sum of all forces, right, happen to be equal to, let's do the normal vector. It's a straight procedure, force of gravity plus the kinetic friction plus force of the applied force that I just applied, Fa. We're always going to select, I need to put components, so I is going to the right, J is going up. So here's mass times acceleration, so let's break it apart into components. So acceleration, it's being pushed this way, so the acceleration is going in that direction, so it's MAI, mass times acceleration, which I don't know. The normal force, I don't know what that is, but I know it's N, let's call it N. It's going up, so it's NJ. Force of gravity is mg, so this is minus mg down minus j, so it's mg. I'll put a parentheses around this. What's the kinetic friction? The kinetic friction says, if you remember, force of kinetic friction is mu k times the normal force. So this force of friction, right, is resisting, so it's going in a resisting to our force that's pushing to the right. So there's a resistance force going backwards, so we're expecting this to be minus mu kinetic normal force. In what direction? It's negative I. It's going the opposite direction. And where's the applied force? It's Fa going forward, I. So we have a vector equation again, and I'm going to reduce this equation and rearrange terms. So I'm going to move the j's together. So this is saying that mass times acceleration times I is equal to j vector, which is the normal vector minus mg plus I vector. So I'll put a parentheses around here. The applied force minus mu kinetic normal. So left hand side equals the right hand side, and that's only possible if the j component is 0 and ma is equal to this. So we have two equations coming out of this, that 0 is equal to n minus mg. Second equation says mass times acceleration, acceleration is what I'm looking for, is equal to the applied force, I know, and then the coefficient of kinetic friction times the normal force. Now these problems, right, initially it seems a lot of labor trying to put this in I and j components, right? But as the problems get more complicated, right, it's best to do this repeated process over and over again of basically drawing a diagram, do a free body diagram, make sure your I and j vectors, your unit directional vectors are written down, and then expand in terms of, in terms of I and j vectors. So the first equation, basically we can see that we get that normal force is equal to mg. So great. The second equation is what we're looking for. So what is the acceleration? Acceleration is the applied force minus mu kinetic. But what's the normal force? Mg. All divisible by m. And we can reduce this. The acceleration is really the applied force over m minus, I cross out the m over here, so it's mu k g. In this case, right, the applied force happens to be 10 newtons. 10 newtons divisible by 10 kilograms minus kinetic coefficient is 0.01 of 9.8. So in that case, right, we have 1 minus, so 9.8 is 0.098. meters per second squared. I haven't really looked at the number of significant digits, and you should really fix that, but I want you to make sure that you understand the idea before you spend time thinking about significant digits. So all these answers, if they were like 3 significant digits, so here I can't really tell if it's like 1 significant digit or 2 because we don't exactly, so we should be writing these in number of significant digits. So all these calculations that I'm doing, right, I want you to get the idea, not worry about the number of significant digits in the answer. Worry about it, so once you understand the concept, right, really start applying the number of significant digits in the final equation here. So the only point the significant digits are important, right, in this last step, which I didn't actually fix. So I don't know if this is 2 significant digits or is it 1 significant digits. I can't tell it's 2 or 1 because we don't know what the mantissa and the exponent is in these scientific numbers. But anyway, so this is the acceleration. The acceleration is 1 minus 0.098. So let's take a more difficult problem, right? So you can see this procedure, right, is a mechanical process, and if you do it properly, right, you're going to see this over and over again. So imagine we have an incline, and we're told, right, that we can change the angle of this incline. We have a mass m, and I'll put some numbers in here. Let's say mass is 10 kilograms. Theta is, it's up to us. I don't know what the angle is, theta. And we're told that the coefficient of static friction is, let's say, 0.1. So I really do have to worry about significant digits, and I really don't want to emphasize it because it's not as important as you understanding the idea. So we're asked, right, at what angle will this object start slipping? So start slipping. Well, whatever. Sliding. And I got a question mark. So we're going to repeat this process over and over again. So we're going to do a free body diagram. But notice that, so we don't know what theta is, and that's what we're trying to find. So we were only told that the mass is 10 kilograms. The coefficient of static friction, mu s, is given 0.1. So again, we're going to do a free body diagram. I'll do it over here. So in a free body diagram, we have the mass. There's a normal force working at an angle, so this is our normal force. So maybe I'll draw a little angle here. So if this is angle theta, this must be theta, so this is our normal force. That's acting, pushing up this way, right? The normal force is perpendicular to the surface. Here it is. We're told that the force of gravity is, well, we're not told, but we assume it's the surface of the Earth. So the force of gravity is Fg. And there is so this object is being pulled down, so there's a frictional force, and you have to know the direction of it, and I'm going to say it's pointing along this line here. So this is the force of static friction, and it's working backwards because the object, if I didn't have this friction, it would be sliding right down the hill, but this incline. But this object is stationary, and because it's stationary, right, the frictional force must be pushing something up. So Fs must be pointing up. And the angle, right, this must be theta here. So this is theta here for the normal force, and this is theta for Fs. And so again, we're going to be starting doing the I. I vector is going to the right, and J vector is pointing up. And so our calculation says that we're going to do sigma F, and sigma F, so I'll write mass times acceleration first, ma, is equal to sigma F, the sum of all forces, second law, but that's equal to 0 because it's not moving. So we're asked what is the angle theta. We don't know what angle theta is. We're going to find it in a sec. So I can then say the sum of all these forces are force of gravity. So there's a normal force, there's a force of gravity, and there's a frictional force. So there's only three forces acting on that object. So there's a normal force plus there's a frictional force Fs, and then there's a force of gravity. And we're going to repeat this process again. What is the normal force? The normal force, right, is acting this way. I don't know the value of it, I'll use the magnitude as n. And so remember, this is I and up is j. So if I want to find the horizontal component, right, this component, then we'd have to say that this is the ratio of this side to this side is n sine theta. So that is, so the horizontal component is the I component, n sine of theta. Actually, let me write it out separately in case I can put it together. So I'll say the n vector is n sine theta, because I don't know what n is. And the up component, right, is j component. I'll put the j first. And n cosine of theta. So this is the up component. What is Fg? Well, Fg is the force of gravity, and it's acting down, so that's minus mgj. It's going straight down, force of gravity, mass times gravity. What is the frictional force Fs? I don't know what the frictional force Fs is, but I can just say it's the magnitude and it's going in this direction. So again, I'm going to be breaking it apart. I know it's going up, so the ratio of the up component to this side is sine, so this is J Fs sine of theta. Now this component is going in the opposite direction, so it's minus I Fs, it's cosine of theta. The ratio of this side to this side is cosine of theta. So I'm going to sum these things up. I'm going to write these up, and actually, because I don't have a lot of space, right, I'm just going to say this is here, this is this, and this is this, and I'll just expand it. So I'll say that 0 is equal to the I component, and I'll just do the calculation as if, so there's an I component for here, so this is n sine theta. There's another I component, which is minus Fs cosine of theta. That's the I component. Here is the j component, plus j. The j components are basically n cosine theta minus mg, and then there is a Fs sine theta. So I've substituted all these vectors into that equation that's equal to 0. Once they're equal to 0, right, I've done broken apart into components I and j. So we have two sets of equations. So it must be that n sine theta minus Fs is equal to cosine theta. So the first equation says that n sine of theta minus Fs cosine of theta must be equal to 0. Because this is 0 vector, so the components must be actually 0. And actually, looking at this equation, I can actually calculate what n is right away, right? It's the, well, actually, it's, well, nf, so let me finish this off. So the next equation basically says that it's n cosine of theta, and I'll put the Fs first, Fs sine of theta, and minus mg is equal to 0. I just rearrange the terms, but we have two equations. So look at the equation, okay? So we're looking for the maximum angle, right, where this equation is always true, the maximum theta. So this is true for any theta. So, so the maximum angle when this equation is true. So what is the normal force? No idea. What is Fs? I'm not sure. This is the kinetic friction, right? So we don't know what that is. And so can I convert this? And I forgot to put one more thing. Of course, we know what Fs is. I didn't write it down, but we also know that the force of static friction is actually mu times n. So if you look at this equation, right, we can actually plug in for mu n here and here. So I'm sorry I should have done that earlier, but anyway, so I'll do it. Let me erase this. I have to erase something. Yeah, I'll erase this. I want to keep the original diagram in. I don't need these equations. I just need this, those two boxes. So we're told that n sine of theta minus, what is Fs? It's mu n cosine of theta is equal to 0. The second one is, so you can actually see that we can actually get an answer really quickly. But the second equation basically says that it's n cosine of theta plus mu n sine of theta minus mg is equal to 0. In the first equation, if you look carefully, right, the n's disappear. We can divide by n both sides of the equation, and you're left with sine of theta minus mu cosine of theta is equal to 0. I'm going to move this term to the other side, and we get sine of theta is equal to mu cosine of theta. I'm going to divide both sides by cosine theta, and you get coefficient. And I've been dropping s constantly. I'm sorry about that. But so that says the coefficient of static friction must be something of sine of theta over cosine of theta. And that's actually tan of theta. And that's it. We didn't even have to look at the second equation. We actually had to just look at the first equation and notice that this is true. And so what is theta? Theta is equal to arc tangent of mu s. So what is mu s? So theta is equal to arc, the inverse tangent of 0.1. And so this is the maximum angle before the object starts slipping. So the coefficient of static friction, right, is equal to tan of theta. So if we increase it by this angle, I don't have a calculator with me, but if you increase it beyond this. So basically this procedure of calculating static and kinetic friction, right, it's a mechanical process, but you're going to have to start getting used to knowing, understanding the problem, drawing a figure, do a free body diagram, and do a sigma F equals ma, the second law of Newton, and then plugging in all the components and getting an answer. It's a mechanical process, but you do have to constantly keep doing it over and over again. Anyway, so yeah. So let's change this problem around a little bit, then ask ourselves, right? If I have an object, so I'm going to say same thing, sliding problem. Actually, let's make it a little bit simpler. Actually, so imagine the following sliding problem again. And I'll use kinetic friction this time. So I won't put any numbers in because I want you to get used to getting units, getting your ideas of components down. So imagine that you have a box again. You're told m is equal to theta, and I want to find the acceleration down the hill. So imagine that you have an incline, a hill. There's a box. You're told that the acceleration of this box going down the hill, I don't know what that is. I'd like to calculate it. Assume that the kinetic friction, right, is mu k, given like 0.1, 0.2, I'm not sure, just something. Somebody tells you this. We're told the mass of the box, if you need it. And what else? We're told theta, the incline angle. But we're told that the object is already moving, so we are using kinetic friction. So again, we're going to repeat this process over again and do a free body diagram. So if you look at it, there's a force of gravity pulling down, Fg, and then there's a normal force that's on the surface, then there's a frictional force. It's sliding down the hill already, right? Then we know that the frictional force, right, is acting backwards. So that's F. But we're talking about kinetic friction, so I'm going to use Fk. So that looks like a free body diagram, but I'm going to be more explicit by not putting it there. I'm going to do a free body diagram over here. So here's our normal force, N. And if you look at the angle, this is theta, so it looks similar like the last one before, it didn't change. Then force of gravity is pulling down, Fg. And then on the incline, right, there's a kinetic force, Fk. And we're told we need to find the acceleration of this object. And if you look at the kinetic force, the sliding force due to kinetic motion, right, this is theta. So this is theta, and this is theta. So again, we're going to find out sigma F, but unlike last time, we don't know what the acceleration is. It's not zero, so we'd like to know exactly what it is, assuming it is the object is already sliding and it's going to be accelerating down the hill. So we write this in expansion. We'll write this as the three forces: normal force plus the force of gravity plus the kinetic frictional force, Fk. That's equal to mass times acceleration. So step number one, we have an equation. Now I'm going to break it apart into components, so we can write this, what is the normal force? Well, this normal force is going this way, and again I'm going to be using my I vector to the right and J vector up. So the normal force, right, I, happens to be going to the right, so this component here must be the ratio of this side to this side, the opposite, so that's sine. So this is n sine of theta I. Now the component up must be n cosine of theta j. Force of gravity coming down, right, must be minus mgj. So I'll put a line there so you can see it better. So you know this is for n vector Fg, and what's the kinetic friction? Fk, and this time, not like last time, I'll actually substitute directly in this time. So this is frictional force, and this is mu n, the mu times the normal force, but this mu n, right, is acting up in the j direction, so let's do that first. So this component here, so that's sine, mu n sine theta j. And then there's a component this way, it's going backwards in the opposite direction and going to the left, so that's minus mu n sine of theta, actually sorry, cosine of theta, and this is I. So I created a lot of space, hopefully. Actually, let me move this over here. So mu k, we're told m, we're given theta. So these are all given, we don't know the acceleration. So I'm going to plug it into this equation, and of course the acceleration, the acceleration is, what's the direction of the acceleration? And here I'm going to actually put it in the free body diagram. Okay, the acceleration is going down this way, and this is angle theta also. So what is the acceleration vector? That's going to be a, to the right is a cosine theta I. Going down is minus a sine of theta j. So we seem to have a big equation. So this is, so mass times acceleration is equal to sigma f. So what is the mass? And what's the acceleration vector? So it's a, so I'm just doing a straight substitution now. A cosine theta, just double checking, and minus a sine theta. Good. So all these problems are very mechanical, but the more difficult they are, right, you can always break these apart into components. And so the easier problems, yeah, it seems like doing this extra steps, but hopefully you'll understand this to solve more complicated problems in future. A sine theta j, and that's equal to normal vector plus force of gravity. So this is me now substituting this in. So this is the n vector is n sine of theta I plus n cosine of theta j. Then we have the force of gravity, which is minus mg j plus, let's put parentheses on this so you understand. And then we have force of friction. Fk is given by mu n sine of theta j minus mu n cosine of theta I. Okay, so if you look at generally the equations, right, we don't know what A is, so that's what we're trying to find. We don't know what N is, so there's two unknowns and we're getting two effective equations. So look at the first, so let me start breaking apart into the I components on this side. So the I component is N sine of theta. Here is also minus mu n cosine of theta. So there's an I component here, there's an I component here, so I put those together. Here's the J component. The J component, so I've done this, so next one is n cosine of theta minus mg plus mu n sine of theta. So this vector here must be equal to this vector, which means that the components must be equal. So we're getting two equations. One says that mass times acceleration of cosine of theta must be equal to this. And the second equation says that minus ma is equal to the j component. In this case, it's n cosine of theta minus mg plus mu n sine of theta. So all of these variables are known, it's just that we don't know what n is, we don't know what a is, and this is what we're looking for, n times a. So we can start doing a little bit of expansion. So I'm going to solve for n in this equation and substitute this equation into the next equation to solve for a. So it's a little bit of work at this point, right? This is not physics, this is straight math. And actually I'll reduce it a little bit, but I don't think this is really that important right now. Once you've broken up the components forms and everything, I think it's enough to actually say that, but the procedure now is just mathematics. So I don't know what the a is, I'm trying to find the a, so let me erase everything. So this is the a acceleration. So look at the first equation. So I have a mass, ma cosine of theta is equal to, I'm going to factor out the n. So it's sine of theta minus mu cosine of theta. The next equation is, I'm going to repeat the process again, ma minus sine of theta is equal to n times cosine of theta plus mu sine of theta minus mg. Now looking at the first equation, this is just a lot of extra work, but the whole point is we have a bunch of equations we can now solve. This is just basically applying mathematics. So we can solve for ma cosine theta, so I'll say that the first equation says that the normal force, right, is equal to MA cosine of theta, all divisible by sine theta minus mu cosine of theta. Sine theta minus mu cosine theta. Now I'm going to substitute this into the second equation. So we can write this now as minus MA sine of theta is equal to the normal force. In this case, it's MA cosine of theta over sine of theta minus mu cosine of theta for n, all multiplied by cosine of theta plus mu sine of theta minus mg. So let me erase all of this. So these are complicated and long equations, but actually, you know what? I'll put dot 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 because we can solve for a. So once we solve for a, we'll get an equation. Of course, I might have made a mistake, and I'll actually go through the calculation if need be, but the whole point is the setup of the equations. So the setup of the procedure, right, whether you're using frictional forces or static and kinetic sliding frictional forces, right, or static and sliding frictional forces, or kinetic forces. These forces, right, are very mechanical. There's nothing special. Even the circular motion that I'll be discussing in another future video, they're basically done the same procedure. So our basic idea is that draw the picture. After drawing the picture, do a free body diagram for all the forces acting on the object. Find the components of each of the forces and substitute them into sigma F equals ma, and then break up into equations that you can solve. And this is the process of solving the equations. Notice that I'm only solving for a, so basically I'd expand and then move everything to one side and then solve for a. Now this process, these are long equations. It's not an easy problem to calculate, but I wanted you to see the procedure in constructing these solutions. Okay, the actual solution itself, right, is not important right now, because I really don't want to emphasize it, because there are better methods than doing this, but they're more advanced in mathematics and physics.